Hello there, this is a lesson on more mechanics, I suppose speed, distance, time, and particularly looking at graphs. And I suppose the posh name for these are displacement and velocity graphs, or you might have called them distance time graphs and speed time graphs. We're going to try and make sure we understand all the important ideas that we need for A-level maths. So what does the gradient indicate? And I'll notice this is what we describe as a travel graph. A travel graph is one that has distance up the side, how far you've travelled, I suppose. And in this travel graph, you'll notice it's kind of the ones that you've got at GCSE, really, no more than that. And it's how far away from home you are. So this graph can go up and then start coming down again if they start going home again. And very often you get graphs like that. And obviously time across the bottom. And the question that it obviously starts to make you think of is what can you find from this graph? And for instance, this question says, how many meters does he travel per second on his journey to get to his friend's house? Now, presumably this is him going to his friend's house, and this is him at his friend's house. It's apparently Bob. So he's at Bob's house all the way across here. That's where he's at Bob's house, and this is the journey to Bob, because he's still moving. It looks like he's 30 meters away. It doesn't seem to be very far. So how many meters did he travel per second? Well, how long did it take him? It took him 4 seconds. So if I was doing this, I'd be doing 30 divided by 4 equals 7.5 meters per second. I'm not sure how the answers come up here. 7.5 meters per second, yes. Notice then that what we're doing really, we're finding the velocity. So what you should learn from this is the gradient is how we find this here, is what we did with the gradient. So how in general can we interpret the gradient of distance time graph? I'd say it's the velocity. Sometimes the speed, if it doesn't care about direction particularly, it can be the speed or the velocity. So one important thing we'll write down in a bit, and you don't need to write it down just now, but basically this idea that the gradient of a distance time graph is the velocity. Okay, what about the gradient of a velocity time graph? We do get these graphs instead of drawing distance traveled up the side, we have velocity. This is a velocity or a speed time graph. Now when you get this, what does the gradient represent? Dave pushes his friend Bob, who's on a wonky skateboard, down a steep hill. There you go. You can see as he's pushing him down, he's speeding up. He was at 4 meters per second. By the end of the journey, he's at 7. Well, is he at 7? Well, no, because he's still moving. He's still moving at 7 meters per second. In fact, all the way down here, he's still moving forward. This is all forward motion. It would have to turn negative. That's meant to say 10, I think, and 11 and 12. It would have to turn a negative speed for him to be going the other way. So that's a subtle difference between velocity and speed, I suppose. This is velocity. This has a direction. What does the gradient of the rate of change represent now? And the answer is it's the acceleration. The acceleration tells us how fast his speed is increasing. So on that basis, state and describe the acceleration between A and B. Now, A and B, so usually you just draw yourself a little triangle here. And you say to yourself, well, his speed has increased by 3. So if I was doing this, I would say 3. And I divide that by how long it takes to do it. It takes 4 seconds. So that's 0.75, or 3/4, I suppose. Notice the units, ms to the minus 2. Sometimes written m stroke s squared. So either of those is good enough. So that's his acceleration from A to B. And it also wants B to C. Where's B? B's there, C's there. No, right. Notice they are straight across. That means his speed hasn't changed. That means his acceleration, his gradient, remember what we're doing here is we're finding the gradient of this line. And the gradient over a line like this is 0. And therefore his acceleration is 0. Basically he's not getting any quicker. There's no acceleration. Now this is a slowing down. That can be called a deceleration, or even a retardation. It's not a word you hear very often, I admit. But this deceleration, what's his acceleration then? Well, draw the triangle again. It goes down 7, so it's minus 7 divided by how many seconds? 2 seconds to do it. So that's got a deceleration, or an acceleration, I suppose, minus 3.5. But you could easily call that a deceleration of 3.5. What did I do? All right, yeah, I called it a deceleration in the answers of 3.5. And notice I've used that notation for units as opposed to this ms to the minus 2. They're exactly the same. So 2 questions for you to do. I'd recommend you pause the video, and I'm going to put the answers up in a bit. I want you to, on the first one, notice this is distance time graph, and distance and time, and therefore when you find the gradient you get the speed. And this is all this is. Find the gradient for these different sections of the journey. And for the second one, notice it's a velocity time graph. So when you find the acceleration, you're finding the gradient again. So it's just a difference of approach. Gradient here will get you the speed. Gradient here will get you the acceleration. So I'm going to pause the video, and I want you to do 6 questions. So I'm hoping you've done your 6 questions. Otherwise, it's pointless doing these lessons. So make sure you have done them, and make sure you get these answers. So for question 1, my answers were 5 northern minus 20. There he is, got a negative speed. And I suppose technically it's the velocity. You could even call that 20, because it does answer the speed, but the velocity definitely is minus 20. And that's a subtle difference between what speed and velocity is, I suppose. And to determine the acceleration from this graph, again, there's 3 things to do. C to D, look at this. Whenever it goes across, you know it's going to be 0. So that one was 0, and these 2, one of them's negative because it's slowing down. The other one's positive because it's going up. Its speed is increasing. So with those 2 questions, 3 important points that I want you to write down. I don't think we've properly written them down yet. Number 1, on the displacement, and this could equally be called a distance time graph. So on a displacement or distance time graph, the gradient gives you the velocity. Now that's one important point. On the second important point, on the velocity, and again can be called a speed, on the velocity time graph, the area under the graph is the displacement. Now this is one that we've not yet seen. We're going to do this properly in a bit. The one that we have seen is that on the velocity, again, or a speed time graph, the gradient gives us the acceleration. So look, we've seen this one. We've seen this one, and this is the new one. This is the one that we're going to have to do some practice of now. So 3 important rules. Make sure you've written them down. Pause the video if you need to. So this idea of distance travelled then is an important idea. And based on what I've just written down as a rule, this is a harder example. It says find the distance travelled here. So if I was asked to do this on this graph, I would split it into 3 parts, because it's not an obvious area to find. Remember what I've said. Distance travelled. This is what we're basically thinking. The distance travelled is the area under this graph. This rule, remember, only works if it says speed or velocity here. If it says speed or velocity, I can use this rule. If it doesn't, if it's a travel graph, it says distance there, the area under the graph means nothing. So what we're going to do is we're going to try and find this distance by splitting it into 3 sections, number 1, number 2, number 3. And I've got these sections labelled over here, number 1, number 2, and number 3. Let's do the area of a triangle first. It's well, you should remember it's half the base times the height for the area of a triangle. So that's 3 across, and what's that? 35 up. So I'm going to do half times by 3 times by 35. And that's 105, so that must be 52.5, I'm going to say. Check my maths because it might be dodgy. Area of a trapezium. Well, again, this has a special formula, doesn't it? You, again, hopefully remember, it's a half of A plus B times H. And if you're not sure what the A and the B represent, A is this height, B is this height, and H is the distance in between. So what's that go up? It goes 35. So it's a half of 35 plus, what's this height? That's 20. Times by the distance in between, which is 3 to 7, is 4. So that's 55 in the bracket, effectively doubled 110. All these are in meters, by the way, because it says its speed is meters per second. The area of a rectangle, well, that's much easier. It's length times width. So if you know your formulas for these things, it's a lot easier. It's 3 across, 20 up. Notice I didn't say it's 4 up. You have to use the units on the squares. So 3 times 20, that's 60 meters. So what have we got? In total, we've got 110, 170. Is that 222.5? Let's have done some dodgy maths. Good, yes, and I've done each section there. You can see the answer, 222.5 meters. So here's a 4 for you to do. Again, I'm going to want you to pause the video, and when you've paused the video, that will give you a chance to do them. But in each case, it says calculate the distance travelled. Notice in each one, it's a speed time graph. It's a speed time graph. It could easily say velocity. Velocity and speed, as far as we're concerned in this sense, is the same thing. But what I want you to do is to work out the distance travelled by finding the area under the graph. Okay, so I'm going to pause the video again, and I want you to do 4 questions for me. So, fingers crossed you've done those 4 questions. And I don't know how well you've done on them. Here's the answers. Right? I do hope you've done them properly, because otherwise, again, we're wasting our time. Here's my 4 answers. So, well, I'm not sure if you can quite see this one. This one says 300 meters. The others you can clearly see are 175, 160, and 227.5. Any of those not sure, ask when we have our lesson. So we've done examples of where they've drawn the graph for us, I suppose, and that's important that we can do it. But we also get questions the other way around, and we also get questions which are, when I say the other way around, what I meant by that was where we have to draw the graph. And secondly, I suppose we also get questions where it's just a wordy version of what we've just seen, but you just have to interpret it. Not sure if this one is. This velocity time graph shows the motion of a car travelling in a straight line for 20 seconds. It starts at rest. Okay. Find the acceleration for each stage of this journey. Actually, this one's a relatively straightforward one. It just wants the acceleration for each section. So already I know this one's a equals 0 because it's not going up or down. This, of course, relies on the fact that I know the gradient of a velocity time graph is the acceleration. We wrote that down just now. So that's what I'm going to use. So if that's a equals 0, what's this one? This is, well, it goes up 5. So it goes up 2 in 5 seconds. So this is a equals, goes up 2 divided by 5 seconds. And effectively, I've just drawn that little triangle there. So this one, how far up does it go? That's the first thing to work out. It goes from 2 to 8. It goes up 6. So a is 6 divided by how many seconds? 5 to 10 is 5 again. So this one, I suppose, is 0.4 if I did it as a decimal. This one is 1.2. And this last one, what's happening here? Well, it goes down a total of 8. It goes down 8 in 5 seconds again. Being very nice. So that's minus 1.6. 0.4, 1.2, 0, and minus 1.6. So did I say 1 minus there? Obviously, yes, I did. It's minus 1.6. And obviously what I need there to make sure is I include the units for all of them. And we're running out of time. Oh, just remember that I did mention this before. Remember, deceleration or retardation could be used to describe this instead. If I did say deceleration, the deceleration would be 1.6. Or it's got an acceleration of minus 1.6. And that's the way to think of it. If you change the word, then you lose the minus. I suppose it's the same as speed and velocity. You could have a speed and a velocity which is the same, or you could have a velocity, for instance, which is minus 3 meters per second, but its speed would still be 3 meters per second. You wouldn't care basically about the sign for the speed, but you would for the velocity. The velocity would tell you whether it's going this way or this way, plus or minus. Look, we've run out of time. I've got a couple more questions to do with you, which we'll do in class. And we've got 2 lots of that. And don't know where that's gone. And then eventually, I'll make sure I sort that out for when we do the lesson. But then eventually we'll do exercise 19D. But I quite like the idea that we've got these 2 proper questions to just remind us of all of this when we get to the lesson. So that's it. Thank you very much, and I hope that makes sense.